So in the group, I posted a question. There you have to use a nodal analysis to find out the answer. So the question is like this. You have ammeter A1, the resistor of 6 ohm, next 3 ohm and 15 ohm, and ammeter A2. Between these two nodes, we have 8 ohm resistor connected, and these two nodes short circuit. They have given information that ammeter A1 reads 1 ampere. So we have a 1 ampere of current flow through this resistor. So we have to find this reading. I mentioned using nodal analysis for this question should be easy. So I'll start. We can start grounding one point, right? Grounding a node. It's convenient. So I'll say this node is ground. If this is ground, here the potential is 0 voltage. Here also it's going to be 0 voltage. Now, when you have a current flow in this direction, so this is 1 ampere, current flow in this direction, you have a potential drop. So the voltage here, V equal IR, applying V equal IR, you should get -6. So across this resistor, now you can find the current in this resistor because you know the potential difference. Using the potential difference, it's 6 volts. 6 is equal to 3I, therefore I is equal to 2. So the current in this resistor is 2. So 1 ampere, 2 ampere together, the current through this is 3 amperes. Because it is 3 amperes, now check the potential drop. The potential drop is 24. So already it is -6. From -6, a drop of 24, that is -30. So now you know the potential difference across this resistor, that is 30. 30 is equal 15I in this direction. So I is equal to 2 ampere. Okay, is the idea of this question clear? Using other methods, using other Kirchhoff's laws, KVL, it might be a bit hard than this KCL. Is the question clear? So in the previous class, we were discussing about potentiometer. That is what we did finally. There, in the primary circuit, in the secondary circuit, we only had a battery with an internal resistance. Okay, so today we are going to have a different circuit. We are going to determine the internal resistance. So determination of internal resistance of a cell. So if we draw the setup, the primary circuit setup is similar. It won't change. So here this is our primary circuit. From this primary circuit, now we connect a secondary circuit. This time the secondary circuit is slightly different. This is the battery with an internal resistance, and it is connected to a resistance box. And now this setup goes through a safety resistor setup and then the galvanometer. So this is E naught, and let's say this is what we are going to find, E that has internal resistance R. So here over here we have a switch. Here we have a switch. So let's say this is K. When K is equal, when K is open, when K is open, just like this, it is identical to the previous circuit, right? That we discussed earlier. You don't have this portion. So it is identical to the previous setup. Then you will get a balance length L naught, a balance length L naught, where it will be the EMF of the battery. The reading will be the EMF of the battery. So when K is open, we can write that E is equal to K L naught. Now K is closed. When K is closed, the circuit slightly differs. K is closed. When you close K, now you will have a current flow in the secondary circuit and you will have a current flow in the primary circuit when it is closed. So let's see, here you have a current flow. Due to that current flow, now this time the terminal voltage will differ. Terminal voltage is not anymore equal to the EMF. So we will get a new balance length. Which will be corresponding to V. So when K is closed, terminal voltage V is not equal to E, since there is a current flow. There is a current flow within the secondary circuit. So that is very important. It is inside the secondary circuit. So E is equal, so we can write E minus, otherwise we can write V is equal E minus IR. No, I, simple now. Okay, V is equal E minus simple R, or V is equal IR. Both of them are correct. Is it clear? You can use the terminal voltage equation E equal V equal E minus IR, or you can use V is equal IR because it is the same voltage across this resistor also. Is it clear? Now we have to find I, but E is equal I R plus R. Therefore, I is equal E over R plus R. V is equal E R over R plus R. But this is equal K into the new balance length, L. It is equal KL. So we are trying to find what is R. Then we can divide the first and the second equation. This is the first equation. This is the second equation. If I divide the I'll divide the first by the second, second by the first. So when I divide, I get R over R plus R. One minute. Yeah, R over R plus R, that is equal L over L naught. L over L naught. So here, what is the dependent variable? What is the independent variable? You change R. This is a resistant box. You can change R. So when you change R, this simple L, not the L naught, L is going to change. So here your independent variable, that is R, and your dependent variable, that is L. So I have to try to get L to the y-axis and R to the x-axis. But you can observe here, you are not able to get R to the x-axis. So let's get the reciprocal. So if we get the reciprocal, we have L naught over L is equal 1 plus R over R. Okay. Now, we can subject 1 over L. So we get 1 over L is equal R over L naught into 1 over R plus 1 over L naught. So this equation is in the form y is equal to mx plus c. This is in the form y is equal mx plus c. So you can get several data points. You can change the value of R, the value of L will change. Using those data points, we can plot a y equal mx plus c graph. So if I plot 1 over L with 1 over R, I must obtain a y equal mx plus c graph. Using this graph, the intercept C and the gradient M. So we know that M is equal to R over L naught, C is equal to 1 over L naught. So M is equal RC. So R is equal M over C. So using this graph, we can find the internal resistance. Now, you might have a doubt. So far, is the experiment clear? Idea of the experiment clear? Shahama and Saja, give the idea of the experiment. Now, did you all have one doubt? When we say balance point, when we say balance point or balance condition, I used to say the current is zero, right? I used to say the current is zero. But here, we have a current flow. So is it, I was having a doubt with how balance condition is achieved. So this is the main doubt, or this is the misconception most of the time that comes in this and previous experiment. So the explanation for this is, look, here you have a separate current in the secondary circuit, and here you have a separate current in the primary circuit. The current at balance point, at each of the balance point, there won't be a current flow into the circuit. If there is no current flow, then there is no outflow of current also. So there is no uh, deflection of galvanometer. The galvanometer won't deflect. The galvanometer won't deflect. It will be pointing zero. Then during the balance point, here the voltage across these 2 points, where it is connected, look, this point is connected here. I'll use the same colors. This point is connected here, and this is connected over here and here. So when you measure the length here and find out what is the potential drop, it will be equal to this potential drop. You have a secondary circuit in this setup, therefore there will be a separate current flow. Thus, this time it is not the terminal volt, it is not the EMF, but it is the terminal voltage this time. Okay, do you get this idea? You understand that there is a current flow, but there is no current flow from primary to secondary or secondary to primary. That is why we get a balance point. Is that idea clear? Three of you? Or should I explain once again? Yeah, I knew. So here, when we say balance condition, if you recall the previous experiment, when we are talking about balance condition, we say the current flow is zero. Okay, clear with that? Just think the switch is open. When the switch is open, there is no current flow here. Have you all drawn the circuit before I make any changes? Have you all drawn the circuit? Okay, so um, now let's think the circuit is open. The switch is open. When the switch is open, when the switch is open, now for the secondary circuit, there is no any circuit where the current can flow, except it only can send current to the primary circuit. But once the balance condition is achieved, current is zero. Okay, once the balance condition is achieved, the current is zero. So there is no current flow. There is no current flow in this secondary circuit at all. Okay with that? Okay with that idea? K is open, no current flow. I is equal 0. I secondary, yeah, I secondary is equal to 0. Okay. Now, when you close this circuit, when you close this circuit, when you close this circuit, uh, whether you have a current flow, whether you have a current flow, whether when there's a balance condition, so now the switch is closed. Now switch is closed. Now the switch is closed. When the switch is closed, uh, you have a circuit where the current can always flow. The current can always flow in this circuit. It doesn't have any relation with this primary circuit. Okay. When I say balance condition, during this situation, balance condition, that means still the galvanometer reading should be zero, right? If the galvanometer reading is zero, then only we get a balance condition. Okay with that? When the galvanometer reading is zero, then only it's a balance condition. For the galvanometer to be zero, galvanometer reading to be zero, this current should be zero. Okay, current to the galvanometer has to be zero. Clear with that idea? Now, can you remember when we have a battery, when we have a battery, the amount of current that is flowing out should enter the battery. Can you remember? So even if we have a circuit like this, we have a circuit like this, will there be a current flow through this resistor? Will there be a current flow through this resistor? No, right? What is the reason? If current flows through this resistor, then the current leaving and the current entering won't be equal. Okay with that? Now, can I have separate battery on this side? Can I have a separate battery on this side and have a separate current flow in this circuit? We can. Still there won't be current through these resistors. Agree. Still there is no current through these resistors. Agree with that. Now, uh, why there is no current flow? Why there is no current flow? Because there is no path for the current to come. And another condition also will be satisfied. The voltage here and the voltage here will be equal. Okay. Let's say the voltage here is V and V1. Here also it's V1. Now take two resistors. So here the voltages are same, V1 and V1. Now here, let's say the voltage is V2. Here also the voltage is V2. Here also the voltage is V2. I connect a resistor. Okay, I connect a resistor. So here there will be a separate current flow. Here also there is a separate current flow. What can you tell? What can you tell about the current? What can you tell about the current in this resistor? In these two resistors. What can you tell about the current in these two resistors? So I have given the voltages on each side. Okay. Will there be a current flow in these two resistors? Will there be a current flow? No, right? There won't be a current flow. There won't be a current flow. The reason the voltages are same. Now I'll put the galvanometer here. This is the galvanometer and I have the resistor. Now what can you tell about the galvanometer reading? Now what can you tell about the galvanometer reading? It is zero. Agree with that. So there is a separate current. There is a separate current in this circuit. There is a separate current in this circuit, but there is no current flow between the circuits. Got it? You have a separate current in the primary. You have a separate current in the secondary. You don't have current between the circuits. I between circuit is zero. Okay. Saja and Shahama, clear. The current between the circuit is zero. So it's a balance condition. Okay, right? Now, look, it is the same circuit here. It is the same setup here. No difference. Here you have a primary circuit and this is a potential divider. Here you have a secondary circuit and here also you have some potential. When these two potential difference are equal, there is no current flow into this circuit as well as there is no current flow out of this circuit. But you have separate current flows in each circuit. So here this galvanometer will deflect for the current between the circuit, not for the current within the circuit. Okay, clear. Sarah, are you clear now? Shahama? So when you do a question, for now you might have a rough idea. When you do a question related to this, or when you revise this note once again, you will understand this much better. Okay. So have you noted these equations? Have you noted the equations or need time? Okay, quickly note down. Should I zoom in? Once you have noted, let me know. Okay, so let's write down below. To plot this graph, we have to vary R, right? How to vary R? To vary R is varied by removing by removing known plugs from the box one by one, and corresponding balance length L is obtained. Okay. Note number one. The galvanometer deflects for the current between the circuits. Okay, between, not for the current separately in the circuit. Second, the balance length L, is a constant while changing R. Then the reasons may be as follows. The first reason may be the infinite plug, the infinite resistance plug may be removed. may be removed in the resistance box.